Now, there's something that's kind of important for you to know at this point in time. This is one of the most important things that you can learn about chemistry. Okay, so here with neon, we have an atom with 10 electrons, and that was exactly enough to fill up the first and second energy levels. And all the orbitals in the first and second energy levels are full of electrons. There's no more than that. There's no less than that. That makes the atom very stable. Other atoms will not have that electron configuration. They'll have maybe more electrons than that, obviously, or they'll have less. Now, what an atom will want to do is it will either want to lose electrons or gain electrons such that it can become a configuration where all its energy levels are full of electrons. So look at sodium here, and we have 11 electrons. You can see that these lower energy levels are filled with electrons. We have the 3s energy level has 1 electron. What sodium can do is it can do this. If it can lose its 3s electron, if it goes somewhere, guess what kind of electron configuration it now has? So now sodium was 11 electrons, but now it's down to 10 electrons. And so it would have a positive charge in this example. When it has lost that electron, look what has happened. Now the sodium ion does have neon's electron configuration, so it's very stable. So by losing 1 electron, it achieves a noble gas, neon's a noble gas, a noble gas filled energy level configuration, and it becomes very stable. Now, is it what we saw with sodium in this example, that it could just lose 1 electron to get that noble gas neon configuration? Is it possible for elements to want to gain electrons to do the same thing, get a noble gas configuration? And the answer is yes. So we have fluorine here, and you can see that fluorine's electron configuration with its 9 electrons is 1 away from neon's stable configuration. So if it can get an extra electron here, it goes there. And so now, before you had fluorine with 9 electrons, I just added 1. And so now it will be fluorine with 10 electrons. I'll put a negative charge here. So this 9 would be changing to 10 electrons. And so now you can see that fluorine with an extra electron now has a noble gas configuration. So now you can sort of see why sodium tends to want to lose an electron and fluorine wants to gain an electron, and why you can form a compound between elemental sodium and elemental chlorine. So what will happen is when you form a compound between elemental sodium and chlorine, they probably will not want to stick together on their own because sodium has 11 electrons and fluorine has 9 electrons. But if sodium loses its 1 electron in its highest energy level, it goes down to 10 electrons and it becomes positively charged. That electron can be transferred to fluorine. It goes from 9 electrons up to 10 electrons and it becomes negatively charged. So when you have a transfer here of electron from sodium to fluorine, both elements achieve a noble gas configuration, and those ions become very stable, and because the ions are oppositely charged, they bind together. So, for example, with magnesium, you could write out the configuration. And so you might recall that magnesium has, the ion has a 2+ charge. Well, magnesium has 12 electrons. I'm not going to write all this out, but what you would find is in the 3s sublevel, there are 2 electrons here in its configuration. So maybe now you can sort of see why magnesium ion is +2, because if these 2 electrons leave, then these lower energy levels are left in magnesium ion and they're filled with electrons. And so it tends to want to lose 2 electrons. Okay, so I want to do a few more examples. And now we're getting into odd electron configurations. Okay, so let's do vanadium. So we have vanadium, which has 23 electrons. So that's a lot of electrons. And so you can work it out, but you will find that the 1s orbital is filled, the 2s orbital is filled, and then the 2p is next, 3s, and then 3p, and then we had the 4s, and then I need a little bit more room here, so I'm going to write 3d. Okay, so we don't need this chart anymore. Okay, so it has 23 electrons, and so 4, 6, 8, 10, 12, 14, 16, 18, 20. And then 21 goes here. And so you might ask, where's the 22nd electron goes? Well, remember that these 5 orbitals here in the d sublevel have exactly the same energy. They're degenerate orbitals, and so Hund's rule applies. And so we put the 22nd electron here, and then the 23rd electron goes here. So this is a correct configuration for vanadium. So it is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d3. So that's pretty cool, right? Or maybe that's not the right word, but that is correct. Okay, so now we're going to go try the next element up, which is chromium. It has 24 electrons, but it's not going to have the configuration that you would expect. So I need to talk a little bit about that. So chromium has 24 electrons, and so the 1s are filled, 2s, 2p, 3s, 3p, and then just for, well, I'll put 4s here is fine. And then I'll put 3d here. And I'll just draw lines here for electrons to speed this up a little bit. Yeah, okay, so here are the electrons filling the 3p. Okay, now we have now an extra electron more than vanadium. So what you would think is that there would be 2 electrons in 4s, and then vanadium with 23 electrons had 3 in the 3d, and so you would expect chromium with an extra electron to have 4 in the 3d. So you might expect this. Okay, and so this is a reasonable expectation. The problem is, experimentally, we have found that chromium does not have this configuration. Instead, it has something a little bit different. And what it has is as follows. What it has is what we have found experimentally. If you look at the 4s sublevel of chromium, it only has 1 electron there. And this electron here is moved down to fill this orbital of the 3d sublevel. So this is actually what I'm writing now is the correct configuration of chromium. 1 electron has left the 4s, and it's gone down to fill the 3d. So chromium still has 24 electrons. They're just not quite in the places where you would expect. So it's 1s2, which is normal, 2s2, 2p6, 3s2, 3p6. This is all like before. And now chromium has 1 electron in the 4s, and it's pushed that other electron into 3d. So it's 3d5. So why did it do that? And what we think is going on is that if you have a configuration that only needs a single electron to completely fill the sublevel, it will take an electron from a slightly lower energy level. So the 3D sublevel has a little bit higher in energy. The 4s sublevel is a little bit lower in energy. But what will happen is because we had 4 electrons to start, we can just go ahead and grab an electron for 4s and stick into the 3D, and now we have completed the 3D sublevel. And when that happens, that lowers the energy of the 3D sublevel even further, even less than 4s. So if you have a half-filled sublevel, or in other words, 5 orbitals, each with an electron, that stabilizes the sublevel even lower to make it lower energy than 4s. Okay, let's do another one, copper. So copper is 29 electrons, and so it's kind of the same deal. So it's 1s, 2s, 2p, I'm getting messy here, 3s, 3p, and then 4s, and then 3d, so 1, 2, 3, 4, 5, 3d. So copper is 29 electrons, so the 1s is filled, 2s is filled, the 2p is completely filled, 3s is filled, 3p is filled. And then how about the remaining sublevels? So normally you would think it would be this. And you can see with 29 electrons, this is what you might expect. But again, experimentally, we don't find that. Instead, what we find for copper, we only have one electron in the 4s sublevel, and we have now a full 3d sublevel for the same reasons as chromium, in that if you move an electron from the 4s sublevel and now fully fill the 3d sublevel, that imparts extra stability to it, and now the 3d sublevel has lower energy than the 4s, and so that will be filled first. So its configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then it's, or excuse me, I made a mistake. It's 4s1. Oops, don't make the mistake I did. Okay, and it's 3d10. Okay, so what I want to do, well, I see that you can't see that. I'll write it up here. It's 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, 3d10. This is for copper. Okay, and so this will have 29 electrons. Okay, so let's move on. Okay, so there are a couple other things here that I want to kind of mention about these irregular electron configurations. And so the ones I just went over were chromium and copper. So this is what you would expect for chromium, but it's not right. And this is the true configuration of chromium, which I went on over the board. Here is copper's configuration that you might expect, but it's wrong. This is the true configuration. And here are some examples of other elements where you have new configurations that you don't expect. And so the basic rule to remember is that if you have, say, a d sublevel that is one electron away from being either half filled or fully filled, it will take an electron out of the lower s sublevel and fill up the d sublevel. So for example, you can see with molybdenum, it has a lot of electrons, I forget the number, but in the outer shell, you would expect 2 electrons in 5s and 4 electrons in 4d, but you can see it's 1 electron away from being a half-filled sublevel, and so 1 electron is taken away out of the 5s, so this is not correct, and so that electron leaves the 5s and goes into the 4d, and so now the 4d sublevel with 5 electrons is half-filled. So you also have weird ones like ruthenium, and so here 1 electron from the 5s is removed to go into the 4d, but it doesn't even half fill it. It still happens. You don't have to remember that one. That's unusual. The only ones you really have to know are the ones where all you need to do is take out 1 electron from a lower energy s sublevel, and if you add it to the d sublevel, it will either completely fill it with 10 electrons or half fill it with 5 electrons. That's the only thing you'll need to know. And we'll probably go over this on some worksheets. Okay, moving on. Okay, so what I've been doing in this sort of presentation is talking about a little bit about the differences between electrons in the highest energy level versus electrons in lower energy levels. So the name of electrons in the highest energy level is called valence electrons. And so if I got sort of a picture of it here, and so because valence electrons are electrons in the highest energy level, they can be found the furthest out from the atom, while the electrons in the lower energy levels are called core electrons, and they're further into the atom. And so one of the things you may have heard maybe from a previous chemistry course is that if you have an atom react, it's usually that atom's valence electrons that are either be transferred to another atom or are being shared with another atom. And you can sort of see why. You would not expect the core electrons to either leave the atom or be shared with another atom because they're further down, but the valence electrons are on the outside of the atom, and so they're far more likely to either be lost by an atom to go to another one or to be shared. Okay, moving on. So you should be able to identify valence electrons and core electrons. So here we have chlorine's electron configuration, and you can see that there are 3 energy levels here. There's a first energy level with electrons, a second energy level, and a third energy level. And so if you were to be asked what are the number of core and valence electrons in chlorine, could you answer the question? So here, if we want to identify the valence electrons, we just look for the electrons in numerically the highest energy level, which is the third. So these are the valence electrons here. And for the core electrons, we look for the electrons in the lower energy levels, the first and second. So these are the core electrons here. So it looks like chlorine, how many total valence electrons it has? It's in any electron in the third energy level, there's 2 in the S sublevel, and there's 5 in the P sublevel. So chlorine should have a total of 7 valence electrons. And so I think I've indicated that there. So you can sort of see here, this is another representation for the configuration of chlorine, which we'll go over. But yeah, it looks like these are the valence electrons, and there are 7 of them. How about calcium? So I'm hoping you can sort of look at this picture and see that calcium has only 2 valence electrons, which are in the 4th energy level. And then it looks like it has how many core electrons? Let's see, it's going to be 2 here, another 2 for 4, another 6 for 10, and then another 8 for 18. So calcium looks like it has 2 valence electrons and 18 core electrons. Okay, so the last thing I want to go over is something very important in chemistry. So you're now at a point in time where you can really understand why is it that elements in the same column have the similar properties. And so why would elements have similar properties? That's a good question to ask yourself. And so what would be the requirements for elements having similar properties? Well, one thing you would want to look at is the ability of an element to react with other kinds of atoms. And so what you may note is that certain elements react with particular kinds of atoms that other elements do not react with. So you see what these similar elements may have in common to react with this particular group of atoms. And so if you look at, for example, the halogens, you probably know already that the halogens, which are fluorine, chlorine, bromine, and iodine, have similar properties. And so now you can understand why. And the basic reason is because all these elements have the same disposition of electrons in their highest energy levels, meaning they have also the same number of electrons in their highest energy levels, so that they have similar reactivities. So let's go over this example in particular. So with fluorine, the highest energy level electrons are in the second energy level, and there are a total of 7 highest energy level electrons, the 7 valence electrons. So let's look at chlorine. If you look at chlorine's configuration, it also has 7 highest energy level electrons, 7 valence electrons. It's just that they're in the next energy level up. They're not in the second energy level, they're in the third energy level. Bromine has 7 highest energy level electrons now in the 4th energy level, so it also has 7 valence electrons. And iodine now has those 7 highest energy level electrons in the 5th energy level. So it also has 7 valence electrons. So all these atoms here have different number of electrons. It's just that it has exactly the same number of electrons on the very outside of each of these atoms. And so because of that, they have the same number of electrons on the outside. They're going to react in the same way with other elements. So that is why they have similar properties. So thank you for listening to all that, and we'll see you next time.